So what I want to do today is to look at the use of these tangent, sine and cosine, these trigonometric ratios, together with Pythagoras, to try and solve some problems involving right-angled triangles, but from the point of view of resolving forces, which you've been doing in mechanical principles. So I'm going to use that method here. Okay? So let's look at this problem. Resolve the force vector of 50 newtons at an angle of 35 degrees to the horizontal into its horizontal and vertical components. So the first thing I'm going to do is to draw a grid, like a set of axes. And my force is going to start at the origin here. And then it's going to go outwards 50 newtons at an angle of 35 degrees. And the first thing I'm sure you're aware of is that by convention, so this is my convention that I'm going to use, angles are measured anti-clockwise from the positive x-axis, which is this axis here, the positive x-axis. So I'm going to start at that positive x-axis and go round 35 degrees, and that's where my force is going to be. So 50 newtons round 35 degrees. So that will always be there. That's the place it is. Not 35 degrees measured from this axis, so going down 35 degrees this way. Not 35 degrees from this axis, 35 degrees from the positive x-axis. If I have a force and the angle is measured as minus 35 degrees, what would I do then? Yeah. So if the convention is angle measured anti-clockwise from the positive x-axis, if I want to go the other way, clockwise, it's a negative angle. So if this had been minus 35 degrees, I'd have gone that way. Okay? So that's the first thing. 50 newtons, then we have measured 35 degrees to the horizontal. I've got to resolve it into its horizontal and vertical components. What that means is I want to find what's the effect of this force horizontally and what's the effect of this force vertically. So what's the component in the vertical? So let's call that the force vertical component and the horizontal component of the force. I want to find out what they are. So what I do is I imagine this line here as being here. So it forms the missing side of a right-angled triangle. So in fact, to do it, I construct a right-angled triangle where this side will be the vertical component of the force and this side will be the horizontal component of the force. So let's construct that underneath. If it's a complicated force diagram, this is a good idea. You know, form the triangle underneath. So this is 50. This is 35. And I want to find FB and FH. So cosine and tangent using this SOHCAHTOA thing, which I hope you all sort of know. Then, to find the opposite side, remember, if this is the angle, this must be the opposite side, this must be the adjacent, and that's the hypotenuse. So I can now, to find the vertical component of the force, I'm actually after the opposite side of this triangle. So the opposite is associated with the sine. You can see that here. So the sine involves the opposite in the hypotenuse. So I'd use that to find the vertical component of the force, and I'd use the cosine to find the horizontal, because that's the adjacent, and so I want the adjacent. So Again, these tell me that sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, opposite over adjacent for tangent. So if I want to find the opposite side, that's going to be the sine of the angle times the hypotenuse, or the hypotenuse times the sine of the angle. This is going to be the hypotenuse times the cosine of the angle. So what do I do to find FV? It's the hypotenuse, which is 50. In other words, it's the force multiplied by the sine of 35 degrees. And then work that out, and I get 28 newtons rounded. So two significant figures there. Okay? And similar calculation for F horizontal. That will be 50 times the cosine of 35 degrees, and we get 41 newtons rounded to two significant figures. So I'll just pause there. So we found the effect of this 50 Newton force vertically and horizontally. So 28 newtons is acting vertically. So this is 28 newtons. And this is 41 newtons. So if I've got a force of 50 newtons acting up here, then I'm going to have 41 of that newtons acting horizontally and 28 acting vertically. And as you've been doing in your mechanical principles, that's really useful, because forces that are at right angles to each other, like this, don't affect each other. So in other words, there's no effect of this 41 Newton force vertically, and vice versa. So being able to separate it out is useful with other calculations. What's the effect of this force vertically and horizontally? Here's another one. Resolve the displacement vector of 40 meters at an angle of 120 degrees into horizontal and vertical components. Any vector can be represented in this way, not only forces. Force is a vector because it has size and magnitude. That's the definition of a vector. So too is displacement. Displacement has size, a distance of 40 meters, and direction, 120 degrees from the horizontal. So that too is a vector that we can represent. Draw the axes. So my displacement is going to start here and then move outwards. But this time, angle of 120 degrees is going to take us into this quadrant here. So this angle is 120 degrees. This displacement is 40 meters, which takes us to here. Useful one, this one, actually, thinking about it while I was waiting for you. If we think of something rotating, so this 40-meter displacement vector could be a rotating armature or something like that. So in other words, it's going round in a circle around, the center point. Okay, well, that's not bad, is it? Okay, it's going round in a circle, and it's reached this point here. And so after a certain amount of time t, it's reached that point, and we might well be interested in that after this time t, how far is it displaced from this horizontal? What's its vertical displacement from the x-axis? What's its horizontal displacement from the y-axis? How far has it moved in this machine part in this x or y direction? So in other words, we might well want to resolve this into its vertical and horizontal components. And so we have exactly the same sort of problem. The horizontal component would be given by this, and the vertical component would be given by this. So again, we've got a right angle triangle. So if we draw the right angle triangle out underneath, you can see this right angle triangle. Let's draw it a bit. So here's our right angle. So this is 40 meters. 40 is 40. 40 meters. And we're after the displacement. We tend to use the letter S for displacement. So this is the horizontal displacement, and this is the vertical displacement, SV and SH. What's the angle? Right, yeah, 60 degrees. So in other words, to find the vertical and horizontal components, we're not using the 120 degree angle. So drawing it out helps us to see the angle we actually need, which is the 60 degree angle. So now again, I'll leave you, work out please the vertical component and the horizontal component of this displacement using the sine and cosine. We know this angle, so this must be the opposite, this is the adjacent, and that's the hypotenuse. So hopefully you got 35 meters for the vertical component of the displacement and 20 meters for the horizontal. Okay. Let's look at this one. A force of 5 newtons is inclined at an angle of 45 degrees to a second force of 8 newtons. Both forces acting at a point. Calculate the magnitude of the resultant of these two forces and the direction of the resultant with respect to the 8 Newton force. With respect to the 8 Newton force means that that's going to be our guideline, our start point, and we want to know what's the angle of that, of the 5 Newton force with respect to that. So if I'm going to draw this, I'm going to start by drawing the 8 Newton force as my sort of datum line, my start point. Everything's going, all angles and all calculations are going to be measured with that as my start point. So we put that along the positive x-axis, 0 degrees in other words. So again, we might draw our grid. And we've got a force of 5 newtons inclined to an angle of 45 degrees to a second force. So 45 degrees to that is going to be my 5 Newton force. And it's plus 45 degrees, so I'm going to go around anti-clockwise following the convention, 5 newtons. So this angle here, 45 degrees. Okay. Let's look at this then. There's 3 ways we can think about this. So let's just quickly resume, or quickly summarize those 3 ways. First way is, and I guess you've been doing this sort of thing with Omal, first of all I could draw the 8 Newton force. So the first way to do this is to draw the 8 Newton force, and then top tail method this is, at the end of the 8 Newton force, draw the 5 Newton force. So I've got a 5 Newton force and an 8 Newton force. And what's the resultant of these 2 forces? The length of that line there. What's the angle of that force to the 8 Newton force? This angle here. So I'm after angle theta and resultant r. So that's one way to do it. So I could construct this and use some sort of scale. Uh, 1 centimetre equals 1 Newton, something like that. So I draw a line 8 centimetres long to represent that force, measure around 45 degrees, draw a line 5 centimetres long, join them together, and then measure this angle theta and measure the length of this line to get the resultant. In other words, draw it to scale. Top tail method. Okay. A similar method, number 2, this is called a parallelogram of forces. You would draw the 8 Newton force, which is this one. You draw the 5 Newton force, which is this one, at an angle of of 45 degrees. So in other words, you draw it as we drew it up here, really, at the start, okay? But then we construct a parallelogram. So I would draw a line parallel to the 8 Newton force, the same length. And I draw a line parallel to the 5 Newton force, the same length. So in other words, that's parallel to that, and that's parallel to that. To form a parallelogram. And then the resultant would be this. And you get exactly the same answer. So again, there's the resultant, and here is the angle theta, which is the angle. So that's the second way to do it. And again, you could do that by drawing it to scale. Draw a line 8 centimeters long, 5 centimeters, and so on. Of course, there's a third method, and I want to focus on that, and that is to calculate it by resolving each force into its horizontal and vertical components and then adding them together. So the third method is the one that I want to look at. Calculate the resultant. I'm going to call the resultant R by finding the vertical and horizontal components of each force and adding them together. So then find the resultant of those forces, and that's the resultant you're after, the resultant. Let's apply this method. I take my 8 Newton force. So I take each force in turn. Let's take the 8 Newton force. That's this one. And find F vertical and F horizontal. Well, this one's actually quite straightforward because the vertical component of the force is 0 and the horizontal component is all acting horizontally, so that's just 8 newtons. So the first one is quite straightforward. And then the 5 Newton force, of course, now is a bit more awkward. So the 5 Newton force, so that was the 8 Newton force, the 5 Newton force is acting at 45 degrees. Is it? Yeah, 45 degrees. And so we can form a little triangle like we've done before and find the vertical and the horizontal components of that force. So just find those for me, please. So we see when we find that out that the vertical components and the horizontal components are the same. They're both 3.53 newtons. So now we can find the total vertical and the total horizontal components by adding them together. So the total vertical component is 0 plus 3.53, and the total horizontal component is 8 plus 3.53. Okay? So the total vertical component is 3.53 newtons, and the total horizontal is 11.53 newtons. So we get the total vertical component 3.53, 0 plus 3.53, horizontal 11.53. So now we can form a triangle. The vertical side of that triangle is 3.53 and the horizontal is 11.53. And if I draw it that way, then we'll get the resultant in the right sort of direction, fitting in with the diagram that we had. So in other words, 3.53 newtons this way and 11.53 newtons this way. So you can draw it out. What I need to do now is to find R, remember that, that's the resultant, and also the angle theta, which is its angle from the 8 Newton force. So how do I find R and theta in this triangle? So to find the angle theta, we use the tangent ratio. Tangent theta is opposite over adjacent, because we know the opposite and we know the adjacent. So therefore theta is the inverse tan of the opposite over adjacent, which is here. So theta is 17 degrees. How do we find the resultant? Use Pythagoras, yeah. Don't use the angle then and then sine or cosine to find it. Use what you know. So use Pythagoras to find the resultant and tangent to find the angle. So from Pythagoras, R equals the square root of a squared plus b squared. That's the Pythagoras theorem. So R equals the square root of 11.53 squared plus 3.53 squared. So R equals newtons. So that's the calculation. So to recap, back to the original question, we want to find the resultant of these two forces, the 5 and the 8 Newton force. So I want to find what's the resultant with respect to the 8 Newton force, measuring the angle with respect to the 8 Newton force. 3 ways to do it. 2 construction techniques where you might do it to scale. The third method is to calculate it by finding the vertical and horizontal components of each one. So we've done that here. The total vertical component and horizontal components of the 8 Newton force is easy. A quick calculation using sine and cosine to get the vertical and horizontal components for the 5 Newton force. So with practice, that's quite straightforward as well. You just then add them together to get the total vertical and horizontal components of 3.53 and 11.53. From that, you construct the triangle. Note how I've made the triangle look like the resultant is going in the same direction as it is in the original problem, which was here. Okay. Construct this way, yeah, the calculation. And then finally, how do we, and get to know these, please. It's always the same with these. If I'm after the angle, I use the tangent ratio, and I use that theta is tan to the minus 1 of opposite over adjacent. So that's a good formula to get to remember. Yeah. No, because if you're looking for the vertical and horizontal components, if you think about it, they're always going to be the opposite and the adjacents, aren't they? If you've got the if you've got this, you've got the resultant anyway. So it's all constructed to find this R. So you won't have R, you'll have this and this. So it's always tangent. And how do we get the resultant? We always use Pythagoras once we've got those other two sides. So Pythagoras and this tangent ratio are used to find the resultants of two forces, 2 or more forces.